So, you studied about the TCP timers in the last class. There is one more important service provided by the TCP, that is called congestion control. You know what a congestion is, right? There is something similar word called contention, there is something called flow control, there is something called congestion. How they are related? What is congestion? Let us say you have something, a sender sends a packet, let us say it sends one packet and that packet is delivered. The number of packets delivered versus the number of packets transmitted, let us say. And we will assume that the subnet or the channel or the network where the packet is delivered has a maximum carrying capacity. Let us say this is the maximum carrying capacity of the network. Now, when the number of packets delivered by the sender is less, definitely they will be delivered to the receiver because they are all below the carrying capacity. And the ideal case is that till the carrying capacity they can be delivered, there will be no packet loss, right. And then after what will happen? There may be a constant flow. This is the ideal case. It's like you have a bucket, let us say you have a bucket and at the center of the bucket you have a hole here. You go on pouring water into this. You may add as many as number of water, does not matter, but the outcome will be always by a drops, right. That means it is a predictable, you can say it is a predictable output. Somewhat we say this is a leaky bucket algorithm. This is usually, the concept is usually used when you have the routing case. That means a buffer or a router may have as many as number of inputs from different sources, but when it forwards the packet, it usually does in the principle of a leaky bucket. It has a predictable source or predictable output through which it has to send the packets with that rate. So, similarly in this case also, if the router gets the packet from as many as number of packets till its carrying capacity, the number of packets delivered or sent out is 100%, but when it goes to the maximum carrying capacity, it is almost like a leaky bucket case, but this again we consider to be an ideal case. Think of, this is if you consider one input, think of number of inputs are, n number of inputs are there to the router. So, what they will do? They will go on sending, the number of packets will be too high, and as soon as the number of packets are very high, it will seem that they are not able to be transmitted and there will be a packet loss, again retransmission, again packet loss, the buffer is not able to handle. So, ultimately your case will be a completely inefficient transmission. That means you have a degradable output, or what we say, this is the usually normal situation. Your packet delivers are really reduced a lot, and if this situation occurs, we say there occurs a congestion. Congestion means you have a channel, the number of packets those are being flooded into the channel is more than its carrying capacity, for which the channel is not able to carry those packets till the receiver, and they are being dropped maybe at the sender side, they are maybe at the receiver side, or even they may be lost on the transmission channel. In any of the situation, you can say there occurs a congestion. So, when we control this situation, you can say that now we have the flow control. So, if you have the flow control, you can control the number of packets transmitted by the sender. Now, till now what we are doing is the window size that we are deciding for flow control was a function of the receiver's capacity, right. Till now we studied that it is a function of the receiver capacity. The receiver decides what will be the window size. If it announces a non-zero window size, the window is expanded. If it sends a 0 window size, it is not expanded. So, that means the receiver was completely handling, or you can say controlling the size of the window for the sender. Now imagine a situation where the receiver sends that I can handle 100 number of packets or segments. So it is understood that the sender should send the fix the window size to 100. Agree? Now imagine sender and receiver part is okay, they understand that I can send 100 segments, and he says that I can process 100 segments by putting them in a buffer and giving to the receiver application. We are forgetting one part in the communication, which is the channel or the network. The network too has got a bandwidth. If this bandwidth is not sufficient to handle these 100 number of segments at a time, and if this fellow sends all the 100 segments completing the window size, what will happen? This 100 will never reach at the receiver, and there will be again packet loss. So in actual situation, TCP, when it decides the window size, what it says, TCP sender window. TCP sender window is a function of, or you can say it is the minimum of the receiver window and the network capacity. So whichever will be the lowest one, the sender will decide its window size accordingly. That means if the receiver says my buffer size is 100 is the buffer size, and the network bandwidth says the carrying capacity says 80 segments at any point of time, then the sender window will be decided with the minimum of 80 and 100. So this will be set to 80. This is how the window size is actually decided at the TCP when congestion occurs or when there is a possibility of congestion. It is not only the function of the receiver, it is also a function of the network capacity. So how this, or what we say, the sender window is the minimum of receiver window or receiver buffer, you can say, and the other one is called the congestion window size. The congestion window size. So how this congestion window is decided? When we talk about congestion window, we talk about the network. So how this congestion window of a network is decided? In TCP, this congestion network is decided with two strategies. One is the increasing strategy and another one is the decreasing strategy. So to decide the congestion window size, the network decides what will be my congestion window size, and to have that it has two strategies, one is increasing, another is the decreasing. To have that, it first says what is my maximum segment size. What is my maximum segment size? Depending on the maximum segment size, it decides its congestion window. So how this increasing window strategies decides the congestion window. Let's say the sender window assumes that whatever data I have, I can incorporate into one segment. Like 4000 bytes is generated, so I can accommodate these 4000 bytes into one segment, right. So he says that my maximum segment size is 1. Let us say maximum segment size is equal to 1. So all of the data are encapsulated into one segment, and that is transmitted to the receiver. Now the receiver, what the receiver does? It sends the acknowledgement, and when the acknowledgement is received by the sender end, what it does? It adds up another maximum segment 1 plus 1, which is equal to 2, saying that now this is my maximum window size. So it sends receipt. That means the network is capable of handling 2 segments at a time. So what it does? It sends the acknowledgement. Now once this acknowledgement comes, now the segment size becomes 2 plus 2, which is equal to 4. So 4 segments are now transmitted. this is how the increasing strategy takes place till the maximum size of the carrying capacity or half of the size carrying capacity is occurred. This is what is the threshold, and this threshold is usually half of the maximum carrying capacity. So, if we explain this in a diagrammatically, if we explain this how this increasing strategy or the decreasing strategy takes place, what it says, if you have a, if the number of transmissions is in this direction and here is the congestion window size, if here is the congestion window size, then for one segment, the first transmission, this remains 1. When it goes to second transmission, this size is increased to 2, because 1 plus 1 is now 2. So, this remains 2 for the second transmission. When it goes to the third transmission, this becomes 4. This is 4, and the fourth transmission, this becomes 8. That means you have an exponential growth of the number of segments transmitted with the number of total number of transmission, or in the fourth iteration you find that the carrying capacity, though it is below the carrying capacity, but the number of transmissions or number of segments transmitted is exponentially grown. So, if I say this is the threshold, if this is the threshold, threshold means the half carrying capacity, let 16 be the threshold, I mean the maximum carrying capacity. So, when it reaches to 8, when the number of transmission reaches to 8, then after the number of segments that is added in the next transmission is not the equal to the maximum transmission, rather it is only one more segment added. So, it becomes now 9. So, in the next transmission, when it is a fifth transmission, the number of segments transmitted is 9. Similarly, for the next one, it will be equal to 6, will be equal to 10. So, your increasing strategy says till the threshold value, the total number of segments that is delivered into the network is exponential, it increases exponentially, and when it reaches to the threshold, automatically only the number of, for each, this occurs for only for every acknowledgement, that means every successful transmission. So, hereafter though there is a successful transmission, but the number of increments in the segment is linear, that is always plus 1. So, if I work on this algorithm, if I write the algorithm for this, let the maximum segment equal to the initial segment, if I say if the maximum segment is equal to, let it be 1, then, so I set the congestion window set equal to 1, right. Then after one transmission, I got an acknowledgement. So, the number of one transmission for one acknowledgement, which is equal to now 2. So, set the congestion window now to 2. Similarly, again for 2 segments and 2 acknowledgements you receive, which is equal to 4. Now, this is equal to your new congestion window. Then 4 segments and 4 acknowledgements you get for that is equal to 8. So, you say now the congestion window is equal to 8, that way that we studied. And then after, once the threshold, this is till your threshold occurs, and then after you have a linear increase. So, there is always a plus 1 for every single number of transmission and acknowledgement. Now, let us say at 16, your maximum what do you say, your threshold, let it be 8, okay. This is your threshold, and after 8 you have 9, 10 and this way. Now, let us say at the 10th window size, when the congestion window is at 10, there occurs an congestion. It may happen, though it is less than the carrying capacity, but there may be an congestion at when the congestion window is at 10. So, then after when the congestion occurs, no more increasing strategy takes place. So, what it decides, the new window will be decided by the decreasing strategy. What it says, earlier my threshold was at 8, so I got an congestion at number 10. You reduce the threshold or the new threshold delta 1 is equal to the old threshold divided by 2, which is equal to 5, sorry, which is equal, earlier it was 8. So, this is equal to now 4, right. So, now your congestion window graph will be something like this. For 1 it was 1, then it was 2, then it was 4. So, at 4 congestion window there will be an increasing linear increase of the number of transmission. So, this is how you can decide, or the designer decides what will be my congestion window size, whether I will keep it at 4, I will keep it 5 or I will keep it at 8. Depending on that, the congestion window size is decided, and this congestion window along with the receiver buffer will decide the sender window size. This is how TCP decides or controls the congestion by considering the network sender capacity, the receiver capacity and the channel capacity or the network capacity. At what point the network can lead to a congestion, that is what is a congestion window size. The receiver window size, sender window size and the congestion window size, and congestion window is handled with two strategies, the increasing strategy and the decreasing strategy. So, it decides how much will be the window size, and accordingly the flow control of the TCP takes place. This is how the congestion control is handled by TCP. So, you studied about the different timers of TCP, the services of TCP, flow control, error control and the congestion control, all those things, right. Now, what are the services? We studied about the services of UDP. So, similar to UDP, there are also the services of TCP. What were the services of TCP, UDP? Sorry, I am not services, operations of UDP. No, refer back to the last class. What were the operations supported by UDP? Encapsulation, decapsulation, multiplexing, demultiplexing, queuing, right. So, similar to that, this should be the operations of TCP operations, right. So, first is like your UDP, this also has the encapsulation and the decapsulation. You have the application layer program or the data that is generated, the process or the message that comes from the application layer goes to the TCP, layer and the header is encapsulated. So, it becomes now one segment message along with the TCP header. The segment goes to the next layer added with the new header or the next header, that is the IP layer, and the new data unit becomes the packet or you can say the datagram also. Then this one goes to the next layer, that is the data link layer added with the header, also the trailer is there, and it goes to it becomes now the frame, right. And this frame now enters into the all along the physical layer, goes there. This is the whole step of your encapsulation, and at this end the decapsulation takes place by decapsulating the header of the DLL, that means the frame, and now the packet comes or the datagram comes to the next upper layer, that is the IP layer, where it detects this is the IP, and when this decapsulates its own header, so now you have the only segment left with you, and this segment goes to the upper layer, and here the again the header is decapsulated and then it goes to the next layer or the application layer, and the whole of the process is called the decapsulation. So, similar to your UDP, TCP also has got the same encapsulation and decapsulation of the data starting from the application layer till the file layer and all the way at the receiver side also. And other services, you know, the queuing also were there, multiplexing, demultiplexing, everything remains same. So, the next operation is queuing, then the next is the multiplexing. When you have the multiplexing and demultiplexing, when multiple processes are open, but only one transport layer protocol is there, only one TCP is there, but multiple processes are there. So, what it does? It takes from all the processes, multiplex them, send them to the receiving layer, I mean the receiving station, and this is the receiving TCP, then it decapsulates them and send to the corresponding processes. This is what the UDP was also doing the same thing, and the TCP also does the same operations like encapsulation, queuing, multiplexing, demultiplexing and all. Other than those services, TCP also provides some extra features or the operations. One of them is the pushing of the data, the push service. You remember there was a pointer in the header field, PSH, right? So, push the data. What is the pushing service provided by the TCP? Let's say you are working on a system and immediately at one point of time you understand that I need an immediate response from the receiver. So, what do? You set, let's say you send a query and press an enter. When you press the enter, immediately your process is executed and you get back the result. So, how it happens? How that response is immediately done when the other things are also executing at the same time? Your normal process is you have a sender buffer, you have a receiving buffer, your buffering takes place at the sender side, the receiver side, all these things takes place and you have the normal process of sending, buffering and the streaming of the data. Other than that, when you need an immediate response from the receiver, what the sender does, sender makes the PSH pointer, the push pointer of the header active. This is set 1, right? And when this is set to 1 and a new segment is created with your new instruction, let us say you press and only enter. When this is set and this is once this is set along with the push button, I mean the push pointer is set to 1, this segment is immediately carried to the receiver side without waiting for the window to be filled. When the push button is on, immediately the data that is given by the sender is encapsulated into a segment even with 1 byte of data or 2 bytes of data, and that is sent immediately to the sender side. And here also it is not buffered in the receiver, rather it goes out of sequence to the receiver side and immediately the response is I mean the segment is processed and you get back the query. That is how when you ask for any let us say you are working on any online reservation system, anything. So, when you give an instant query, immediately you get a response saying that this is the availability status, this is something, all those things. So, those are possible only when you have a push service active in the TCP and instantly out of sequence segments will be processed. Otherwise, we know that because TCP is a stream data service, every time the segments are processed in sequence. It does not entertain any out of sequence segments, but only when this push is set to 1, you can have an out of sequence segment processed by the receiver and get back the result. That is one of the very important operation provided by TCP. And another pointer in the header, if you remember, there was a urgent bit, right? Let's say the sender is sending a data, sender is sending some data and the receiver is processing, and after sending some data, the sender somehow realized that my data is being wrongly processed by the receiver. Fine. So, what it has to do? It has to stop the processing, it has to send some messages that you do not process my data anymore. But by the time it realizes that it has already sent some data to the receiver, that means they will be definitely processed by the receiver. What is the option left with this fellow? It can send a, let us say, control C message, CTRL plus C. I send this message. Being a user, you press control C, it has to be aborted. But if you press this, if you send this control C, this will be added to your normal data in the segment and it will be added at the end. So, all the data that you have sent will be processed by the receiver, and at the end only the control C will be processed because they are arrived at the end, right. Now, in that case, how the sender can handle such situation? So, this is something an urgent message to be sent by the sender. So, what the sender does, it sets the urgent URG pointer is set to 1. What the urgent pointer says? It says the address of the last urgent byte. Do you remember? It says the last address of the last urgent byte. So, what it does? It makes or it builds up a segment keeping this control C at the beginning of the segment, setting the urgent bits to 1, and rest of the things could be anything, normal data in the segment. It could be the normal data, does not matter. Now, this segment is transmitted, and to have this out of sequence service or to attend this segment, what it can do? It can also set the push button PSH set to 1. In that case, what will happen? This segment will arrive out of sequence to the receiver, and when it goes to the receiver, that means this segment will be processed by the receiver first out of sequence, and within the segment you have an urgent pointer. And what is the urgent data at the beginning of the segment is control. So, immediately if it says to abort the process, whatever processing was taking place at the receiver side will be aborted and your network resources, computer resources, everything are safe. So, immediate response, you want to have something out of sequence, set only the push data. But if you want something to be immediately done, response has to be, any process has to be taken care of, it is urgent. So, instead of that you go for a urgent data set. Once this is set, automatically your urgent bit will be identified by the receiver, and what the receiver will do, irrespective of other processes, it will consider as a out of sequence segment. In that sequence it finds the urgent data and process it, aborting the whole of the process. There could be many situations like this. So, these are the two extra operations supported by TCP for which it is more popular than the counterpart, the UDP, right. So, TCP services, TCP operations and the TCP timers and the congestion control, everything is done. So, what is left with? Only TCP design. Everything you are studying is a design, IP design, ARP design, UDP design. So, TCP must have a design, different modules, how the TCP is designed. So, at the end we have the TCP design. What are the modules of TCP or how the TCP actually plays the role? It has got 5 modules. The first module, or it is a main module. This module is associated with all other components. One is the transmission control block or TCB, the transmission control block. It has an input processing module, it has an output processing module, and above all it has a set of timers. This you know already. This is a set of timers. So, your main module, the transmission control block, then you have the input module, the output module and the set of timers. So, when the message comes from the application layer, it activates the main module. The main module is activated when you have a process or a message generated at the application layer and that comes to the main module. This is usually activated with the help of the transmission control block. This is a most important part of this. What the transmission control block or the TCP says, and of course there are certain things like you have the TCP segment that comes to the next layer, that is the lower layer, the IP layer, and also there are something that goes to the lower layer, that is the TCP segment, it goes to the next layer, that is IP layer. Fine. So, the one of the most important part is the TCB, the transmission control block, and this is like your routing table, the control module, the control blocks. This is also a table consisting of several inputs or informations about the TCP, the sending process and the receiving process, and it decides actually the status of the whole of the TCP work. So, one of its entity or the entry is, it has got multiple entries. One is the state. The state decides whether the TCP is in the lesion mode or it is in the closed mode or it is in the established mode. The different modes you now understand. It is established, both the sending process and the receiving process, they are active and they are connecting to each other. Closed, the process is not started, it is in the closed state, and it is the listening mode, just started and trying to connect with the other end, the client or the server. Then the next entity is the process. As you know, TCP can have either a client process or it can have a server process. The process can have two options, a client or a server. Then another entry is the local IP address. How it gets it? It gets from the lower layer. The sending process or the sending TCP gets it from the lower layer and it says that what is my local IP address. So, this is always for the sender. And what is the process number? That is the port number, the local port number. So, everything is entered into this TCP, saying what is my lower layer is IP address, what is the process ID that I am using, whether the process is in any state, active state or not, or established state or not, and then also it also gives the information about the remote IP address. This is for the receiver. What is the remote IP address where I want to communicate or the connection has to be established. Along with the IP, that is a socket address, nothing else, this is also the socket address. Along with this, you have the remote port number. So, that means you have the socket address for the sender, you have the socket address for the receiver. Both these values are entered into the TCP. And what is the local window size? This holds the information about the sender window, right. Then another is the remote window information. This says about the receiver window. Then another is the sending sequence number. You know, remember that ISN, initial sequence number, and how the sequence numbers are updated with the segment size. So, sending sequence number, what are the sequence numbers that are being sent with every segment. Similarly, the receiving sequence number. What it carries? Receiving sequence number means it should be the acknowledgement, because acknowledgement also carries a sequence number saying what is the next sequence number expected. Then you have the round trip time. What could be the possible round trip time for this, and what will be the timeout value. Then the buffer size and the buffer pointer. So, these are the informations usually stored in the TCP to say all the details about the processes active, all the processes that have been closed, or all the processes that have been already established and communicating with each other. So, this TCP it usually controls the main TCP. The main module is controlled totally by the TCP. And then you have the input process, as we saw. The input process, Usually the input process what it does? It handles the all this acknowledgement, the TCP that comes to it and sends to the main module, and the checking for whether the port is active or not, and it sends back the, if any error message it sends back saying that this is not active. And you have another timers, already you know the different timers. So, with the help of different timers how the TCP works. So, when the main module works with this, it takes the help of different timers of the TCP and the control block, and accordingly your input process and the output processes are activated and they execute. This is all about your TCP, the transmission control protocol, and why it is popular or why it is mostly used other than UDP. You still use UDP, but where you use UDP now it is clear for you, where you use TCP it is clear for you, right. If you cannot have a segment or if you cannot have a chunk of data, go for UDP irrespective of the reliability and all, but if you can chunk the data, I mean if you can create the small segments of data, go for TCP. It is always reliable, providing all the services of data, flow control, error control, congestion control and other features. This is about your TCP.